the introduction, I will briefly talk about the background of Hurricane Juan. In September of 2003, Hurricane Juan caused extensive damage of forests in Point Pleasant Park, with 70% of forests destroyed. Before Hurricane Juan, the forest type is matured over mature with barely any regeneration. After the hurricane, restoration of park took 9 months, consists of the preservation of young trees and removal of majority of dead trees to reduce the risk of fire. But some of the dead trees were left on the ground to allow for decomposition and supply to nutrition to the soil. This park has been a place of recreation for the citizens of Halifax since the city's founding in 1749. Before that, it was a hunting and fishing place for the indigenous Mi'kmaq people. The site was traditionally a significant Mi'kmaq gathering place known as the spiritual place. The dominant forest type is Acacia forest, which is composed of a mixture of coniferous and deciduous trees. The Point Pleasant Park has a much higher tree diversity than how normally Atlantic Acacia forest type looks like before disturbance. Our goal for the study is to investigate the secondary succession process of mixed Acadian forest type in Point Pleasant Park after Hurricane Juan in 2003 by tracking changes in tree size, community composition, species disturbance, abiotic property, and community marks. Our hypothesis is that after the disturbance of Hurricane Juan in 2003, the Point Pleasant Park has undergoes secondary succession, which lead to the gradual increase of species richness and the number of mean species increase with a decrease of average tree size in past 20 years. Eventually, it will reach to a mixed succession stage.
Design and methods. So the sites were picked at these 6 locations because they were recorded to have the most trees knocked down immediately after the hurricane's passing. We can infer from this that these places were hit the hardest by the hurricane and that they will have the greatest viewing of succession. Materials used. The materials used include a flexible tape measure, a 1 meter squared wooden quadrant, a brightly colored object, and an iNaturalist or species identifying field book. For data collection, in each study site, all living trees greater than or equal to 2.5 centimeters in diameter at breast height will be measured and identified. At breast height is measured to 4.5 feet off the ground. In each study site, the percent cover of each species of ground flora was sampled using 12 haphazardly placed 1 meter squared quadrants. The wooden 1 meter squared quadrants were used to delineate the sampling area. The 12 quadrants were divided over 6 groups to select the sampling area. One group member stood on the edge of the forest plot and threw a brightly colored object over their shoulder. Where the object landed was the center of the quadrant. Once all the species were identified, their percent cover was estimated. The object was thrown again, but from the spot of the first sample collection, and this was repeated for a total of 12 times per study site per year. Regression analysis. We paired the most recent data with the past data collected for the study dating back to 2004. The recent data was compared to the data collection in 2004 using regression analysis on RStudio. Regression analysis was chosen from the form of statistical test because we are looking at the relationship between more than one variable to determine if their differences can be due to random chance or if the differences were due to an outside factor.
The overall forest community is changing towards younger and smaller trees over time, but our data collected in 6 study sites of Point Pleasant Park in the recent 20 years after hurricane disturbance, the diameter of breast height of the trees is decreasing within the forest community. We use regression analysis on average diameter at breast height of the trees over the years, and there is a significant negative relationship. This negative relationship indicates that the tree size is decreasing since the disturbance, and the fast-growing early succession species are dominating the study sites. So over time, the forest may transition back to its climax species as these pioneer species are outcompeting, but initially, smaller short-lived trees were dominant. Currently, the forest is at intermediate stage, where there is more complex plant species than pioneer stage like young trees that provide better shade and habitat. As the forests mature, competition for resources like light, nutrition, and space increase. This benefits slower-growing, shade-tolerant species with the potential for higher DBH. The relationship between DBH over the years will then have increased potential trend when the forests mature into a climax community, a stable late succession stage dominated by huge older trees with higher DBH.
How has species richness changed over time? Regression analysis was used to study the relationship between species density and the years after Hurricane Juan. There was a significant positive relationship between species density and year, with a p-value less than 2.2 times 10 to the negative 16, indicated in Figure 3. Therefore, species density can be predicted from the year studied. With the regression equation, species density is equal to 0.5294 times the year minus 1059.4. Species richness over time was due to external factors and not random chance. This is because our p-value is less than 0.05. We can infer that species richness will eventually taper off and reduce the slope of the graph as it reaches its climax community. This is due to competitive exclusion found in later periods of succession.
In this slide, we will be examining how the density of dominant species, particularly red spruce and red maple, changed over time from 2003 to 2024, and the reasons behind these changes. The disturbance caused by Hurricane Juan significantly impacted the forest structure and succession. We're focusing on how these changes manifested in red spruce and red maple. As we see here in the graph, there is a linear increase in red spruce density over the years with a positive trend. This gradual rise reflects in its shade tolerance, allowing it to thrive as the forest canopy began to recover and close over time, favoring later successional dynamics. In this slide, we'll be focusing on red maple density from 2004 to 2024. Red maple, being an early successional species, showed a different trend compared to red spruce. After Hurricane Juan, the canopy openings created ideal conditions for red maple to thrive, resulting in a significant rise in its density, particularly after the year 2010, and it peaked around the years 2018 to 2019, where you see the most red maple trees, as shown in the graph, with a clear upward trend and a R-square value of 0.1549, indicating a strong correlation over time. Red maple benefited from the sunlit open areas created by the hurricane, which is typical of early successional fast-growing species. However, as the canopy began to close and the succession progressed, the conditions for red maple started to become less favorable, leading to some fluctuations in its density. As the forest moves towards a more mature or climax, we expect some significant shifts in dominant species. For red spruce, which is known for its shade tolerance, the trend should show an increase in its density. This species lives or thrives in shaded, stable conditions and is likely to outcompete others as the canopy becomes denser. This aligns with findings that noted that the shade-tolerant species benefit from less light disturbance. On the other hand, red maple, which flourished in the open sunlit areas following disturbances like Hurricane Juan, may see a decline in its density as a fast-growing early successional species thrives in highlight environments. But as the forest canopy closes and the availability of light decreases, red maple might struggle to maintain its numbers. Future growth would depend on new disturbances that can recreate the conditions under which it originally thrived. From our analysis of the data, it is evident that the successional dynamics in Point Pleasant Park have evolved significantly since Hurricane Juan. The disturbance initially shifted the forest structure, opening opportunities for certain species to thrive, particularly those suited to early successional stages, like the red maple. Based on observed trends, we can conclude that the Acadian forest in Point Pleasant Park is currently in a mid-succession phase. The mix of shade-tolerant red spruce and sun-loving red maple demonstrate a balance between early and late successional species. These are characteristics of a mid-succession dynamic. Urban environments like Point Pleasant Park introduce unique challenges that can influence forest succession. One major factor is soil compaction, primarily caused by high foot traffic and vehicle movement. Soil compaction reduces soil porosity, which hinders water infiltration and restricts root growth. This can limit the establishment of shade-intolerant and pioneer species, which typically play a crucial role in early forest succession. In urban parks, infrastructure like roads can significantly change the light distribution, which in turn affects forest succession. Open sunlit areas tend to encourage the growth of opportunistic early successional species, while shaded dense canopy areas limit the presence of shade-intolerant species. In Point Pleasant Park, we see this pattern, where clearings near roads support a different mix of plants. Past research highlights how changes in light availability can shape the successional pathways of forests. The concept of two-eyed seeing, introduced by Mi'kmaq elder Albert Marshall, encourages us to see the world through both Western scientific and indigenous perspectives, combining the strengths of each. In the context of Point Pleasant Park, applying two-eyed seeing means integrating traditional ecological knowledge with modern science. For example, the indigenous concept of Natukulimk emphasizes using the natural resources provided by the creator sustainably, ensuring the well-being of both the community and the ecosystem. By blending these approaches, we can promote a balanced, long-term strategy for forest management, avoiding over-extraction and fostering resilience and diversity within the park.
Thank you to the many students and researchers alike that helped produce the results for this long-term succession experiment on Point Pleasant Park.